One thing we might find appealing about alkynes is because they have a carbon-carbon triple bond, we can think about adding hydrogen to them to produce either an alkane, which is fully saturated, or an alkene, where we've only added, for example, one equivalent of H2 to the alkyne to produce an alkene. In this video, we're going to discuss methods to reduce alkynes to alkenes and alkanes, using not just catalytic hydrogenation. There's a stereochemical issue that comes in when we convert an alkyne into a cis or trans alkene via the addition of hydrogen, and we're going to learn two methods for cis and trans alkenes via syn and anti addition that use two fundamentally different sets of reaction conditions and two fundamentally different mechanisms. But let's start with the most basic reaction here, which is the full-blown blasted with hydrogen hydrogenation of alkynes with H2 and a platinum or palladium metal catalyst. This reaction cannot be stopped at the alkene stage. The catalyst is just too good. The alkyne reacts to produce the alkene, and the alkene very rapidly is reduced further, all the way down to the alkane. So two equivalents of H2 add, and we get the alkane from the alkyne. If we make the catalyst worse, we can get this reaction to stop at the alkene stage, and this is done by so-called poisoning of the catalyst. The most common method uses what's called Lindlar's catalyst, palladium together with calcium carbonate and a little bit of lead-4 oxide. You don't need to remember the specific chemical makeup of the catalyst. It's completely fine to just write Lindlar rather than this chemical formula. We still use dihydrogen as the source of the H's, and this occurs in a stereospecifically syn manner. So we get the cis alkene from the alkyne in this reaction, always, since both hydrogens add to the same side of the alkyne, in a sense. And so we get the cis product via syn addition. If we want the trans product, we need a fundamentally different approach, which we're going to look at now. If we want to convert an alkyne into a trans alkene, we have to use fundamentally different reaction conditions involving ammonia or an alcohol as the proton source and an alkali metal in the elemental metallic form as a reducing agent. This is known as dissolving metal reduction. We use reaction conditions, for example, sodium metal in liquid ammonia, that produce dissolved electrons and actually dissolve the metal. This is why it's called dissolving metal reduction, to produce these dissolved electrons. And the net result here, if we add in an alkyne, is trans addition of two hydrogens to produce the trans alkene via what we might call anti-addition of the two hydrogens. These reaction conditions produce so-called dissolved electrons, and you can think of these mechanistically as literal electrons that can add to the alkyne. This is what happens in the first step, and we get what's called a radical anion. So we can represent that single electron as E-. E- donates itself to the alkyne with cleavage of one of the alkyne pi bonds, and we end up with an anion on one carbon of the alkyne and a radical on the other. Each of these so-called fishhook arrows is showing the movement of a single electron, and so you can follow these to see how we get two electrons together on this carbon to create a new lone pair, and one electron here to create a radical. This is known as a radical anion. At this point, NH3 gets involved as a proton source, and this was liquid ammonia, so extremely high concentration of NH3 in the liquid state at very low temperature. It's certainly acidic enough to be protonated by this very, very basic carbanion, and that gets us to this radical. Now this radical can undergo further reduction by more dissolved electrons. We're going to use an excess of sodium metal in this reaction to get an excess of dissolved electrons, and we can just imagine one of these dissolved electrons just popping onto that radical center to create now a more conventional looking, I'd say, carbanion, right? Alkenyl carbanion like this. This remains very, very basic with respect to NH3, and so it can deprotonate NH3, and the result is the alkene. Now this doesn't explain the trans stereoselectivity of this reaction. And I would say this is not 100% clear, the origins of the trans stereoselectivity. It may have something to do with the fact that in the radical anion, these electrons prefer to be as far apart from one another as possible because like charges repel, right? These negative charges repel. And so once the negative charge has shown up here and we've protonated and kind of locked in this carbon, the other carbon very quickly undergoes reduction to an anion and protonation and kind of gets stuck in this configuration with the second hydrogen, the second proton, if you like, being added on the opposite side from where the first one was. It all comes down to electron-electron repulsion in this radical anion. So overall here, if you want to generate a cis alkene from an alkyne, we're going to use catalytic hydrogenation with the Lindlar catalyst. And you're more than welcome to just write Lindlar here. H2 you do want to write because that's a reagent we're using, and just Lindlar instead of the chemical formula here. This is a poisoned palladium catalyst. If you want the transalkene from the alkyne, we use dissolving metal reduction with something like sodium metal and liquid ammonia. And if you want to generate the alkane, well, we've kind of already seen this reaction. We just treat the alkyne with H2 and an unpoisoned metal catalyst, platinum or palladium works great.